Welcome and thank you for downloading this TU Delft podcast.
The last lecture to finish, and then I'll continue with this lecture, so I'll hurry a bit up. No. So first, summarizing the result of last lecture. The last lecture was aiming at the equations of compressible flows. So lecture before we derived the equations for incompressible flows, that's for low speed subsonic flows. Then last lecture it was on compressible flows. And then of course density can change and temperature does change. I got quite a few questions on how can temperature not, so how can temperature, please? How can temperature change in an isentropic flow? Because we were able to derive the equations, but we had to assume isentropic flow. An isentropic flow is adiabatic flow, and that means we don't add heat and extract heat from it. And then how can temperature change? Well, not by adding or subtracting heat, but internally in the flow temperature can change. And actually, if your flow is fast, supersonic, transonic, you have pressure and density changes such that the temperature does change in your flow. So through P is rho RT. And it can expand, for example, very much, so the density can drop a lot, and then something will happen to the temperature as well. So please bear in mind, isentropic flow means that the temperature, there's no heat added or subtracted, but the temperature can change. And the other thing is that it should be reversible so that dissipative effects can be neglected. And then we derived these equations. So we had already conservation of mass, the continuity equation. Then last time I derived the isentropic relations, and these are strong relations relating the scalar quantities, pressure, density, and temperature ratios to each other. So once you have knowledge about state at point 1, and you know one other at another location, point 2, you can derive the other one. And these are the isentropic flow relations. Then for isentropic flow as well, we could derive the energy equation, starting from the first law of thermodynamics and using the Euler equation. And this is sort of the equivalent of Bernoulli. Here you see that velocities scale with enthalpy. So velocity squared, changes in velocity squared, scale with Cp times T, and that is enthalpy. And this is conserved throughout streamline, so Cpt plus a half V squared is constant. That's the energy conservation. And we already had introduced the first lecture equation of state. P is rho RT. So we have here the unknowns P, rho, T, and V. So 4 unknowns and 4 equations. So you can, if you know, for example, the areas, you can solve from these anything. And that was where we ended up doing stuff. Last lecture, I was halfway this exam problem of last year. It's a compressible flow problem. If you look at the old exams, typically for the aerodynamics part, we have usually one question on incompressible flows, CL, CDs, and one question on compressible flows. I will not promise anything, but it will be quite a part because it's quite important for aircraft aerodynamics. It will be an important part of the exam. So the exam question we asked last year concerned the supersonic wind tunnel blowing from a large reservoir into a converging nozzle. Reservoir conditions were given, temperature in the reservoir, pressure in the reservoir. Then the temperature in the test section was given the mass flow and the specific heat coefficient and the ratio of specific heats. Then we finished A, so we calculated the air temperature in the throat, and this is a picture of the case. So we have a very large reservoir up here. Flow is going out into the throat. I got also a question, how can the speed be 0 in this large reservoir? Well, you can assume it to be really huge and this to be very small. And of course, in some bit of the reservoir, flow will flow out, but the very large bits doesn't really notice. So you can approximately assume the speed to be 0 inside the large reservoir. It's going through the throat, converging nozzle, diverging in a test section here. Now, if it is, the conditions are such that you get really to supersonic flows, and it was said it is a supersonic wind tunnel, if the conditions are such, and that depends among others, on this contraction ratio, but also on the pressure behind this. Please note that the pressure in the reservoir was 9 atmospheres, so it's really pushed out. If it's supersonic, then at the smallest cross-section, which is called the throat, we will have the Mach number being equal to 1. And the Mach number is speed divided by the speed of sound. So here, the flow will exactly have the speed of sound. And that has to do with something we will explain to you the next year, compressible aerodynamics. If you are more used to partial differential equations, you can see that inside the partial differential equation, that is sort of contained. So it is physically sort of a physical fact that happens. So m is equal to 1 here. Of course, the speed of sound, which we derived last time as well, square root of gamma RT, the speed of sound is depending on the temperature, so can change as well throughout the flow, right? We always work with 340 meters per second, but that's the speed of sound at standard sea level air conditions. In oil, it is different. If you give the air a speed, also the speed of sound changes. So please be aware that you always have to compute that. And then, so Mach is 1 here, sonic flow, and then if it's a supersonic wind tunnel, if you increase the area, the flow speed will increase, and you will have supersonic flow here at the test section. So we're halfway, I think. We just calculated the airspeed as well, and I think we're now at point C. So I will give the answers we derived last time. So the temperature in the test, what was it? In the throat, I think. What was the first question? Yeah, temperature in the throat. So A, T star was 1000 Kelvin. And B, the speed in the throat, actually equal to the speed of sound in the throat by definition, was equal to 640 meters per second. Now let's continue with question C. And the question there is, calculate the Mach number in the test section. Mach number, any ideas how we can? Yes. So step 1, what is the Mach number? Speed divided by the speed of sound. So Mach number in the test section, V test over A test. Now, was there any information that we can use? Temperature. So we know temperature test. So what does that mean? What can we derive from that? Speed of sound. Perfect. A is square root of gamma RT, so we can derive the speed of sound. So that means this part we know. Now only V test. Any idea how we can find the speed in the test section? Yes, perfect. Energy equation. That's relating temperatures to velocities. We have quite some information on temperatures, so probably we can derive velocities. So, and then use energy equation to find V test. Okay, let's try. So first, AE test. So A test is then equal to gamma 1.4 R 288 temperature given 310, right? So that's the easy bit. We find then that the speed of sound is 353.5 meters per second. Okay, now the energy equation. The energy equation was CPT plus half V squared is equal to some other CPT plus a half V squared at different locations along a streamline. So where What is a good idea from where to take the temperature, the energy equation? Throat or the reservoir? Okay, we have some votes for the throat and some votes for the reservoir. So of course we're looking for the test, so we can, this is what we're looking for, so 1 part test. We can do the throat, or we can do the reservoir. Who votes for the throat? Who votes for the reservoir? Okay, more for the reservoir. Both is actually fine. We need the temperature and we need the speed. We have the temperature and the speed in the throat. Perfectly fine, it works. Reservoir, we have the speed, almost 0, so we can assume 0, and the temperature, it will work as well. So both will work, only one is a bit less work, namely the reservoir, because we don't have to compute half v squared, but both is perfectly fine. So you can do this, or as long as a streamline goes through it, because we integrated it along a streamline, and streamlines of course go from the reservoir through the throat to the test section. So both is actually perfectly fine. Okay. And I chose the reservoir. So we have CPT0, and then V0 is almost 0, so that's equal to CPT test plus a half V test squared. So V test is equal to CPT0 minus CP test times 2 square root. So that is equal to 2 times CP is 1008. T0 is given there, it's 1200 Kelvin. And T test is given 310. Square root. And then we find 1,339.5 meters per second. So that you can accomplish, right? So from 0 in the reservoir, due to this very high pressure, so we have very high pressure in the reservoir, we can get to almost 1,400 meters per second. Almost there, because the question was the Mach number, right? So for the Mach number, we have to divide V over A. I'll do it up here. So Mach number test is V test divided by the speed of sound in the test section. V test we just derived. And the speed of sound we started with 353.5. So the Mach number is 3.79. And what is the dimension of the Mach number? It's a dimensionless number, right? We divide speeds over speed. Okay, any questions about this? No? Then we can continue with part D. The area of the throat of the cross section. Any ideas? Maybe I should. Rho AV. We can use that one. And what is it equal to? Huh? To rho AV. Mass flow, perfect. So indeed, rho AV is constant. Good point, because this is the only equation we have the area in, so good starting point. So this is constant. And what is it equal to? It's equal to the mass flow. And you can check it, because if you're interested in what is it, so we have rho, kilograms per meters to the third, area, right, meters squared, v, speed, meters per second. So what is the dimension of this? It's kilograms per second. So how much kilograms of air go through this area per second? Right? So it's the mass flow. Do we have information about the mass flow? Excellent. 0.5. So indeed, we can solve this question now, because we have 0.5. Where do we have 0.5? Everywhere. It's constant. Okay. Area of the throat in the cross-section. Well, then, of course, this one is given. Speed is 0. Whoa. Wait a minute. So we have to apply this in the throat, right? To find the area of the throat. Then somebody said speed is 0. Wait a minute. I'll get back to that. So yes, you might get in the idea that the speed is 0, because of course in the reservoir the speed is 0. We just assumed. So if you apply it there, we have no mass flow. What is happening there? Well, we have an infinite area in a way. So infinite times 0, what is it? It depends a bit on how it goes to 0. So that is not something that it brings you much further. Yeah? So mass flow, rho star, A star, V star. We're looking for A star. So that's going to be the area of the throat. Is then mass flow divided by density in the throat, speed in the throat. Do we have the density in the throat, and do we have the speed in the throat? Speed, yes, right? I think we computed it here. So that one we have from B. So V star from B, V star was 640 meters per second. So if there's any way to compute rho star, we're done. Isentropic relations, perfect. Because isentropic relations relate ratios of something to ratios. So what would you apply it to? So of course on one side density, right? So the isentropic relations for density, rho 1 over rho 2 is equal to, and what would we choose? Which form? Pressures or temperatures? Temperatures, perfect, because we have more information on temperatures actually. So T1 over T2 to the power 1 over gamma minus 1. Now, we have to choose point 1 and point 2. So where are we going to take it from? So this is the general form of the isentropic flow relations. We're looking for something in the throat, so it probably makes sense to choose one of them in the throat, right? So let's do this one in the throat. And the other one? 0, yes, reservoir. Why? Why do we choose the other one in the reservoir? Yes. Sorry? No, this is fine. No, the gamma is with the pressures. Sorry. Something wrong? Yes? Yeah. Sorry. So rho, I made a step. So rho over rho 2 to the power gamma. So the isentropic relations, rho 1, rho 2 to the power gamma is equal to T1 over T2 to the power gamma over gamma minus 1. What I did is I took the square root gamma, the gamma square root of this. Yeah? If I had taken the pressure, of course it's true, but I'm looking for density versus temperature. Okay, why reservoir? We have also temperatures in the throat, right? We need pressure, because for rho 0, it's not enough to have temperatures. We use the equation of state, and we need pressure, and that's the only location that we know of pressure. Indeed. So rho 0 from the equation of state. So P0 over RT0. So let's do that first. Then rho 0 is equal to the pressure, 9 atmosphere, so 9 times 1.01 10 to the power 5, divided by R, 288, times temperature in the reservoir, 1200. So then we find the density in the reservoir to be 2.64 kilograms per meters to the third. So we know this one, rho 0, we know that one, and we know that one. Okay, so now it's just working our way through the equation. So this means that rho star is equal to rho 0 divided by T0 over T star to the power 1 over gamma minus 1. And that's not so interesting, so rho star is rho 0 we just computed, 2.64 divided by T0 was given, 1200. T star we computed at some point, right? Yeah, 1000 Kelvin. So this is from A to the power 1 over gamma minus 1, so that is 1.4 minus 1. And then we find 1.674 kilograms per meters to the third. Oops, are we done now? Almost, huh? Because the question was the area in the throat. Mass flow we had, speed we had in the throat. Now we know the density in the throat, so now we can find the area through very simple relation. So A star is equal to m dot over rho star V star, so that was a half. Rho I just computed, 1.674. And V we had from earlier, 640. And then we find 4.67 times 10 to the minus 4 meters squared. So 4, almost 5, 10 to the minus 4 meters squared, or 4.67 centimeters squared. So the area is like this. So really a very strong contraction. So that you will see quite often for supersonic flow. If you look at our hypersonic wind tunnel, we have a wind tunnel where we can obtain a speed in the test section of 11 Mach 11. We have a very strong contraction ratio. Also the flow expands very strongly, and then the flow condensates, so we can only measure for 1 millisecond. Yeah, is this clear? Any questions about this? So maybe for some people. Okay. Okay, then we continue with the rest of the lecture. If you want to, no, I think we put it already on Blackboard, but I'll check. On Blackboard there are all the exams, and both the questions and the answers are there. So I should have told you before, you don't have to copy. Okay. Compressible flows. a little bit of compressible flows, and what we're then going to do is look at measurement of flows, because that is quite important in our wind tunnels, of course, but also when you're in your aircraft, you would like to know the speed of your aircraft, and we do that in a certain way. So the rest of that, the lecture will be on, first, a bit more compressible flows. I'll derive the second form of isentropic relations, but also how to measure flows. And first, I'll clean the blackboard. And that is section 4.9 to 4.14 of Anderson. So. So measurement of airspeed and the second form of isentropic flow relations. Of course, compressible flows, unfortunately it's not flying anymore, but it's relevant for supersonic flows. So supersonic aircraft Concorde. Just summarizing from last time, also please don't forget about the speed of sound. That's the speed at which sound waves travel. A squared is dp over d rho. And from using the Euler equations and the conservation of mass, we could derive that that is the same as A is square root gamma P over rho. Using the equation of state, we found A is square root of gamma RT. So speed of sound, which travels through a medium, is only related to the temperature. And that's due to the fact that the temperature is actually the kinetic energy of the molecules, and sound is transmitted through molecules throughout the medium. And this is, of course, only in a perfect gas, because we use the equation of state in a perfect gas. Then the Mach number, V over A, we already worked with it. Speed over speed of sound. Well, if Mach number is smaller than 1, then the speed is smaller than the speed of sound, and we call the flow subsonic. We have actually the name also for low speed subsonic. Then we mean really so low, the speed is so low that you can assume incompressible flow, so the speed is then below 100 meters per second. But of course we have also high speed subsonic, so subsonic flows above 100 meters per second. And this 100 meters per second is approximately Mach 0.3. So low speed subsonic incompressible flow assumption about when Mach is below 0.3. But when Mach is between 0.3 and 1, you do have relevant density changes already, but the flow speed is, of course, still below the speed of sound, subsonic. Then Mach is 1, they're exactly equal. Sonic, what you have inside the throat of a supersonic nozzle, a wind tunnel, or also can be a rocket engine. If it's a round one, we also have a certain name that's called transonic. So it says In some parts of the flow it's below 1, in some parts of the flow it's above 1, but it's actually around 1. And that is what most commercial aircraft lines are flying at. So transonic flow, if you have an aircraft at cruise speed, you typically have a speed of about 0.7, 0.8, and then the flow will increase over the wing, and you will have locally supersonic flows on certain portions of the wing. So transonic. Then, of course, if the Mach number is larger than 1, then your speed of the flow is larger than the speed of sound, and we call it supersonic flow. And then we call for really much, much faster than the speed of sound hypersonic. So our hypersonic wind tunnel actually goes up to Mach 11. And that's quite relevant for really spacecraft, not so much aircraft. So this is the range, and of course you can have portions. So in transonic flow you have portions of subsonic flow and portions of supersonic flow. And if flow is speeded up, it goes typically isentropically, so it expands without any shocks. So you can go from subsonic to transonic, sonic, supersonic. But if your flow then has to decelerate again from supersonic to subsonic, the way that works is with a shock. And a shock is a very discontinuous, very sharp location where all your properties jump. Temperature, pressures, velocities, and that is not an isentropic effect. So you can only apply the isentropic relations up till a shock, but not over a shock. Over a shock, actually your total temperature and everything changes. Okay, now let's go to back to now the low speed range, the subsonic low speed, and look at how we can actually determine airspeeds, because that's what we're often very interested in. Speeds of aircraft, airspeeds in our wind tunnel. So how do we go about that? So suppose again a wind tunnel, but now a subsonic nozzle. So we have a converging, diverging nozzle again, a test section here, certain conditions upstream, certain conditions downstream, and certain total conditions in a reservoir way up here. What is then the value of this airspeed here in the wind tunnel section? So I have an example with that, and that's example 420. So in a low-speed wind tunnel, we put a manometer, and actually a mercury manometer, and we connect it to the settling chamber, the reservoir, the reservoir, and the other side we connect it to the test section. The contraction ratio of the nozzle is given, 1/15, so that's the area ratio. The reservoir pressure and temperature are given, and the height difference of mercury is given, where one side was connected to the settling chamber and the other side was connected to the test section. Density of the mercury is given. So question, calculate the velocity in the test section. So question 1 is, what does a manometer do? I hope you'll remember from high school, but if not, I'll repeat it. So let's first start with a manometer, which is a way to measure pressures. Manometer is a U-like tube. We connect the sides through tubes to certain locations in the wind tunnel. One is the settling chamber and the other side is the test section. Then if these pressures, so we have here mercury, if these pressures are not the same, we will get a difference in height, right? Because on both sides we have pressures pushing, so we have a force on this. The force is P1 times A. Here we have P2 times A. And if they're not equal, so if you think about the balance here at this location, then the total force here is this P2 at this location, A, plus the force from the mercury column. and the force of the mercury column, so the force of this part. Anyone remember? Rho GH. So this is an H. Rho GH times something, let's see, force. We need force, right? Force is M times A, right? Mass times acceleration, mass times acceleration, let's call it G immediately. What is the mass of the column? Of this column of mercury? Rho times volume, right? So mass, density times volume, and then still times G. Right, that was mass. Density is kilograms per meters to the third. If we multiply it by the volume of the column, we have the mass again. What is the volume of the column? H times? A times H, perfectly. Yeah, because we have a column here. It's H high, and it has an area A, so the volume is A times H. So the force is rho AH times the acceleration G. So we still have an A in here for the force, right? Now, the thing is in rest, so if we look at this height of this one, we have an equal force pushing here as pushing here. So the forces on the left side are P1A, balance of forces. On the right side we have P2A pushing, plus the force of this column, so plus rho GH times A. Now you see, indeed, we have everything. The area of the tube is not so interesting, the area of the manometer, so it drops out. So we see that P1 is equal to P2 plus rho GH. And this is the G, acceleration here at Earth, gravitational acceleration, and this is the H of the height difference of the column, and this is the rho. What rho is this? Mercury, yes. Sometimes people say, rho, I have a density of air, and they plug the rho in. So this is, of course, we're looking at inside the manometer, so it's, of course, whatever liquid is in there. It can be something else, but we have now mercury. So what does a manometer actually tell you? It tells you something about pressure differences, right? That's what we're typically looking for, because it's low-speed subsonic flow. Once we know pressure differences, we can transform it to velocities through Bernoulli. So this is a very handy tool, a manometer, because we know P1 minus P2 is equal to the density of our mercury or liquid times G times H. Now, do we have, what were we doing? We're trying to calculate the velocity in the test section. Any idea how we can find the velocity? What relation would you first think of velocity? Yes. Yes, very good idea. Can we use the Bernoulli equation? First check, so good idea, velocities and pressures, Bernoulli equation. Only we have to have low speed subsonic flow. Well, it says here low speed wind tunnel. It is not, so it is true, right? Low speed is given. I would recommend, once we have calculated the speed in the test section, which is the fastest section in a subsonic wind tunnel, to check, right, if it's not way beyond 100 meters per second. But good point. So Bernoulli relates pressures to velocities. So that is P plus a half rho V squared is constant. P plus half rho V squared is constant. From where to where are we going to do it? Well, we have some information about state 1 and state 2, right? P1 and P2 through the mercury. Because the mercury gives here it's given the height difference and the density, So we say P1 plus half rho V1 squared is equal to P2 plus a half rho V2 squared. And we're looking for the velocity in the test section, so V2. So we can rework this. A half rho V2 squared is actually equal to P1 minus P2 plus a half rho V1 squared. Now, so we're looking for V2. We need the density in the air. Do we have any idea on the density? Does it say anywhere sea level? So question 1, that's the easiest way out. Do we have sea level conditions somewhere? No, eh? Not saying that we have sea level conditions, so no standard sea level conditions. So how can we then get to the density? It's where we have the pressure? Pressure difference? Equation of state, perfectly. The pressure difference, so if you think about the isentropic flow relations, P over P and T over T, that's really for compressible flow. So that's where you have significant temperature changes. In incompressible flow, you typically don't have them. So the one I used before, right, for the supersonic wind tunnel, that will not get you anywhere. But the equation of state, P is rho RT. So if we know somewhere pressure and temperature, we can find the density. Do we have somewhere pressure and temperature? Reservoir. Or, well, settling chamber it's called here. Yeah. So rho from equation of state. That's settling chamber. Okay, so rho we know. P1, PT, P2 we know through the manometer. So then we still have one equation with two unknowns, V and V. And it's a bit misleading maybe. Low-speed subsonic wind tunnels are much different from supersonic wind tunnels. Supersonic wind tunnels work with a huge reservoir under very high pressure, and then the flow is really injected through a very strongly converging, diverging nozzle. That's typically not how subsonic wind tunnels work. Usually we have a fan and we pump air around through a converging, diverging nozzle, which is much less strongly contracting. And also we don't typically have a large reservoir or something. It's really flowing through. So this picture I showed you here before is really what it works. So really not, so we have here a cross-section and here a cross-section. So we have here certain pressure and here a certain pressure. And what you will see, we didn't compute it yet, but that this pressure difference is not in the order of 9 atmosphere. It's much smaller in incompressible flow. Small pressure differences scaling with velocity differences. So we still have a V1 and we have a V2. We're looking for V2 here, but we have still two unknowns, so we need more information. Question, what didn't we use? Yeah, V1A1, mass conservation. We have actually here. So if you're stuck, read again the question. Is there something given I didn't use? Yes, the contraction ratio. So conservation of mass, continuity equation. And we have incompressible flow, so we have V1A1 is V2A2. So we can substitute this into the equation. We're looking for V2, so we can substitute V1 is V2A2 over A1, right? So we can substitute that into this. And then we have it. So the steps we went through is manometer gives us pressure difference. Bernoulli relates pressure difference to speed squares. Density from location 1. Because we have pressures and temperatures there, equation of state. And then finally we use the continuity equation. V1, A1 is V2, A2. Okay, so let's quickly do it. It's not so interesting anymore. So we have half rho V2 squared is equal to P1 minus P2 plus a half rho V1 squared, so that is equal to A2 over A1 squared V2 squared. Then we collect all the V2s on one side, so we get a half rho minus a half rho A2 over A1 squared times V2 squared is equal to the pressure difference P1 minus P2. Yeah? And that simple. So V2 is equal to P1 minus P2 divided by a half rho, so dividing by rho times 2. And then we have here 1 minus A2 squared over A1 squared. Square roots. Yeah? And this is how actually velocities are measured. So if you know pressure differences from manometers or pitot tubes, as I will explain in a minute, if you know contraction ratios, so areas, and somewhere a density for incompressible flow, you're there. You can apply this relation from Bernoulli and find it. So now it's simple substitution. Well, we didn't compute the P1 minus P2 actually here. It is 1.33 times 10 to the power 4 newtons per meter squared. So what you use here is the rho mercury, which is given there. 1.36 10 to the power 4 kilograms per meters to the third. You use the gravitational acceleration at Earth, 9.8 meters per second squared. And h was given to be 10 centimeters, so 0.1 meter. Yeah? So if you put that in, you find that the pressure difference is 1.33 10 to the power 4 newtons per meter squared. So way different order than supersonic pressure differences of really something with like 9 atmosphere. Okay, so then we have the 1.33, that's here, the pressure difference. 33 10 to the power 4 times 2 divided by the density. We didn't compute the density yet. So let's do the density from the equation of state. So rho is P over RT. Pressure is given 1.1 atmosphere, 1.1 10 to the power 5, R288, and the temperature is 300. So the density then is, where is it? Here. 1.29 kilograms meters to the third. And please don't mix up density. So this is of course the density of the air going through. We use the density in a manometer of the mercury. So 1.29 for the density, 1 minus contraction ratio. That was given 1 over 15 squared, square root, and the end result (144 meters per second). Somebody says, whoo, compressible, yeah. So this is a bit a nasty example. I won't do this in the exam to you because you cannot actually solve it. We didn't give you the information for the compressible flow, but it's very good that you're aware because it's probably, I will show you later what difference it makes quite often. But this, so the speed is above 100 meters per second. Should have used compressible. I should have. Yeah? Later we'll look into the differences actually. It is not a very discrete difference. From the second form of the isentropic flow relations I'm going to derive later, you will see that it's not a strong difference, so it might change 7 or 8%. But I'll do that after. One question? Yes, I'll lift the blackboard up. And have a good break and see you after. I put the manometer on, right? And it's P1 minus P2 with a height. How did I know which one was the low pressure and which one was the high pressure? Because I think I said P1 minus P2, or did I say P2 minus P1? P1 minus P2. So here was rho GH. Could I have said P2 minus P1? No, because you have to realize which one is the low pressure and which one is the lowest pressure. The one with incompressible flow, the one with the largest area, right? So I use this. So A2 over A1 is 1 over 15. So the area 1 is 15 times larger than area 2. So area 1 is the large area. Area 2 is the small area. So area 1, large area, low speed. And then incompressible flow, we decrease the area, the speed increases, right? So area 1, large area, so what I use is A1 is 15 A2. So V1 larger than V2, and then in Bernoulli, of course, P1 plus half rho V1 squared is P2 plus half rho V2 squared. So if V1 is much larger than V2, P2 is much smaller than P1, right? So I drew this one, right? P1, P2. So which one is the high pressure? P1 is the high pressure in this case, and P2 the low pressure. No, it's wrong, sorry. I'm confusing you. Well, doesn't help. Well, whatever. But please, sorry, it doesn't help. But be aware that you do the P1 and P2 correct. Sorry. What you could also have done is, with the pressures, what you could also have done is substitute them, right? So compute P1 and compute P2 separately and substitute them in the Bernoulli equation. Oh. Sorry. That's more confusing. Okay, then speeds. But at least you should be aware which one is a higher speed and which one is a higher pressure and a lower pressure. Speeds. Of course, the notation is a bit confusing. I introduced speed as a vector with a direction, right? Here, I always do a one-dimensional balance. So my speeds, my velocities here have just one direction, typically horizontally. And so I don't assume changes also throughout my cross-section. So I have a cross-section, and I assume unidirectional, uniform flow. So viscous effects is not important, and that is my speed. So it is not really a vector because I use scalars on the other side, so I really use the one, it's only the x direction. Then I asked you a homework, I gave you homework which you can now maybe solve. So given this example, homework 4.4, concerned also, please have a look at it. Was also a converging diverging nozzle with here V in and a pressure 2. A contraction ratio is given there. And P1 minus P2 is given here. It is in Anglo-Saxon units, you can transform it to SI units if you want, but it's more about the way you think. So I don't mind what the answer is, but think about whether you can solve this. The question is to find the V2 only given this. And some people were not able to solve it, but you can solve it a similar way as this example. So please try that at home. Okay. Then we go to equivalent airspeed. And I'll introduce that to you based on another example. Because how is airspeed usually measured on an aircraft? Using pitot tubes and pitot static tubes. And here we have some information. So an altimeter says the aircraft is flying at 1500 meters. We have an outside temperature, 277 Kelvin. If a pitot tube mounted on the wingtip measures a certain pressure, what is the true velocity of the airspeed and what is the equivalent velocity of the airspeed? Now I'll introduce those concepts to you now. So first the pitot tube. That's a way to measure. We had the manometer measuring pressure differences. The pitot tube also measures pressures. The pitot tube is like this. You have the flow. This is actually very small tube. So flow flows into the tube and you have here a pressure gauge, sort of reservoir, where the speed is collected. So the speed goes in, and then the tube fills itself with air. So what is the pressure that you measure here? Sorry? Stagnation pressure, indeed, because it fills itself and then it doesn't flow through. So actually the speed inside this tube, so if you put this tube into the flow, this pitot tube measures the stagnation pressure, or total pressure, there where the speed is 0. We also have pitot static tubes, and that is connecting this one to another with typically a manometer. So suppose you have a channel, you connect this, again, differential pressure gauge now, to this tube. And in this way you can measure differences, right? So here you can measure total pressure, and then here static pressure. Why does it measure here static pressure? Well, this tube doesn't fill up. The flow goes just past it, and inside the pitot tube then it is felt, sort of the pressure locally at that point. So you have then the static pressure and the total pressure, and you have here a differential pressure gauge, so this one measures differences, right? So you have information on P0 minus, well, P static at that location. Okay, so now we have here a pitot tube, so we know the total pressure. Question: velocity of the airplane. Any idea? Yeah? Use V plus P. P plus half rho V squared. Bernoulli is a suggestion. So use Bernoulli. Why? P plus half rho V squared is constant along a streamline. Well, that would bring us somewhere because we have some information on pressures, right? We have the pressure measured by the pitot tube. So we have one pressure. Do we have another pressure? Yes, standard atmosphere. 1500 meter altimeter, standard atmosphere, but not the standard atmosphere at sea level, of course, but at 1500 meters. So we have P0 from pitot tube. And we have a pressure from standard atmospheric table, Appendix A, 1500 meters. Okay, so we apply Bernoulli. So we have P0 plus a half rho V0, and V0 is 0, squared is P plus a half rho V squared. V we're looking for, P we can find from the table. And this table gives you that the P is 8.6655 10 to the power 4 newtons per meter squared. So this one says V squared is P0 minus P divided by rho. So we have the pressure difference, P0 minus P. P0 from the pitot tube and P. What about rho, density? What would you do with density? Equation of state. Yes, very good point, because the temperature is given, right? So you might be tempted to look in Appendix A for the density as well, but we have here more information. So the more actual information you have, you should use it. And why is it given here, the temperature? Temperature is much more easy to measure. How do you measure densities? It's very hard, but temperatures are always monitored, so always measured. So the temperature is given, so we find rho from the equation of state. So rho is T. So rho is P over RT. The pressure is given there. So please be aware, you use that pressure, 8.665. Sorry. Oops. No. The temperature is not measured in this point, but is measured. Oh, sorry. So then, what pressure do we use, right? The strange thing is that the density we assume constant, the pressure changes a bit, so apparently the temperature also changes a bit, but we don't have information on how the temperature changes that bit, right? So what do? We have information on pressures at free stream conditions. So we use the temperature at free stream conditions. So we need the free stream pressure, P, so that's this one, at 1500 meters, right? at free stream conditions, 0.456 10 to the power 4, divided by R 288, temperature given 277. So then we find the density for 1.064 kilograms per meters to the third. So now we can compute the velocity, square root of 2 times P0 minus P over rho. So V is 2 times P0, the pitot tube given up there, 8.6655 minus this one, 8.456 10 to the power 4, divided by the density, 1.064 square roots. And then we find the speed to be 62.8 meters per second. Is that okay? Yeah, so we could have used Bernoulli's law, so please check. Question? Yes? Sorry? No, you don't know if it's incompressible. So in this case, you had to assume. In the exam, I will give you more hints or will write subsonic, low speed. Good point. Is this typically done at an aircraft? Sorry, yeah, question? No? You sure? Yeah?
Why did you use 288 and not 287?
Oh, why did I? Oh, yeah, good point. 287. Yeah, it's not. It is 287 point something. Yeah, sorry, good point. I think Anderson mixes them up now and then. I'm not going to shoot you if you do that.
The pitot tube just measures the static pressure or the difference between them both?
No, the pitot, so question of the definitions, good point. Pitot tube always measures total pressure. So pitot tube is this one. Total pressure. This is the pitot static tube. So this one is called pitot / static tube. So the pitot tube measures total pressures. Now the equivalent airspeed, so we just computed the true airspeed. Equivalent airspeed is, if people are lazy, they sometimes use it in aircraft and they use not the density, the actual density, so not the measurement of the temperature, but the density at standard sea level conditions, so 1.225. So it's approximation. Now how far off are we? So we could have computed the equivalent airspeed. So equivalent airspeed so then if V is 2 P0 minus P over rho S. And this is at standard sea level conditions, square root. And if you put that in, so that is 1.225 kilograms meters to the third. If you would have put that in, you find the equivalent airspeed of 58.5 meters per second. So how much difference? So we just computed 62.8, 58.5, so about 93% of the actual value. So we're off about 10%. So that's equivalent airspeed. Questions? No, then we can continue with our compressible flow stuff. Yes, question, sorry.
Why do we actually use equivalent airspeed? I mean, it's...
Yeah, because it's an Anderson book and it is a good concept. I don't think you use it it that much. The question was, why do you use equivalent airspeed? Well, it's hard to measure densities, but you can derive densities from temperature. So if you have an actual temperature measurement, it's not a problem like this. But sometimes people don't have, and then they use it as an approximation. But especially close to stall, I wouldn't recommend it. Okay. Yes, isentropic flow relations. So bear with me for the last quarter of an hour. Okay. So, what are we going to do? We're going to derive, we have the compressible flow equations. We are actually fine. Energy equation relating temperatures and speeds, isentropic flow relations relating density ratios to pressure ratios and temperature ratios. But sometimes it's easier to work with things like the Mach number. So you can recombine these equations into a different form. They're not more information, just in a different form, which might be handy if you have information about Mach numbers. So what we will work our way towards is, instead of temperatures and velocities and pressure ratios, density ratios, temperature ratios, combine them and say, okay, it would be nice if I have information on a temperature ratio and a Mach number. So I can directly relate ratios to Mach numbers and work that way. So that's what we're going to do. Recombine the equations. And which equations? The energy equation and the isentropic relations later. Now suppose that we have the energy equation, CPT plus half V squared is constant, and you fill in, as we did before in the supersonic wind tunnel, the reservoir conditions here on the right. So the total conditions, then V0. So you find CPT0 is this one, CPT1 plus half V1 squared, right? Drops out. So indeed, here is, in a way, a temperature ratio, right? We can divide now by T1. However, note that this is not a general temperature ratio as in the isentropic flow relations, but here I really have assumed stagnation temperature for one side, right? So it's really T0. So T0 here, T1 here. So I divide by T1, then I get, and I divide by CP, so CP times T1, this one becomes the 1 here. I divide this one by CPT1, so I get V1 squared over 2 CPT1, and here I get CP drops out, T1 over T0. So a temperature ratio, total temperature over a temperature at some point, is equal to 1 plus the speed at that some point, divided by 2 CPT1. At this point. And look what we have here. So T1, wouldn't it be nice? That might be related to the speed of sound squared, right? A was square root of gamma RT. So A squared is gamma RT. I don't have the gamma and R yet, but suppose I have here also a constant. So suppose I can rework this gamma and R into this. Then this T can be A squared, and I have V squared over A squared, so Mach squared. So the only question is, what is here in front? How do I get from this CP to gamma R? So that's what I'm going to do on the blackboard. That's a few intermediate steps. Yes. Yes. Sorry? Huh? Oh, on the screen. Ah, okay. Yeah, I hate that. So I'll upload the one on the blackboard with the written. I have the written version from last year. But that pen is just terrible. I don't think they replaced it. Okay, so we need to rework CPs and gammas. Well, where do I start? We have a relation between R and CP, namely R is CP minus CV. If you forget this, not a problem, because you can actually find it from this one. We had H is E plus PV. Enthalpy is internal energy per unit mass plus pressure times specific volume. H was CPT. E was CVT. P times specific volume. Pressure over density. That's from the equation of state. RT. R. Temperature drops out. So R is CP minus CV. Yeah? Step 1. We need to work our way to CP. What we'll do now is divide by CP. R divided by CP is equal to 1 minus CV over CP. Is equal to 1 minus 1 over gamma, actually. CP divided by CV is equal to 1 minus 1 over gamma. Multiplying by gamma, so we get then gamma minus 1 over gamma. So what I did, starting with R is equal to CP minus CV, divide by CP. So R over CP is 1 minus CV over CP. Then I realized this CV over CP is 1 over gamma. 1 minus 1 over gamma. And then I put them all in 1. So I say, okay, this 1 is gamma over gamma. So gamma minus 1 over gamma. So what is CP actually equal to? CP is equal to R divided by that one, divided by gamma minus 1 times gamma. So, so this CP here, I'm going to replace by gamma R divided by gamma minus 1. But of course I have to divide over it, so the gamma R turns up here, gamma minus 1 there. So reworking this pressure specific heat coefficient, I get to this version. And now see, here's my A squared, right? My A1 squared. So I have V1 squared over A1 squared, so Mach number squared. So this is a very nice form. So T0 over T1 is equal to 1 plus gamma minus 1 over 2 Mach 1 squared. So given a total condition and given a certain temperature at a point, I can find the Mach number at that point. Now that's nice. Of course, this is then temperature ratios with this total condition here relating to Mach number. I also have the other isentropic flow relations I can use. So from these density temperature ratios, I can find density and pressure ratios as follows. So just plugging this in, so I have a relation for T0 over T1. So then I find that P0 over P1 is that relation to the power gamma over gamma minus 1. There you go. And for rho 0 over rho 1 to the power gamma, it's equal to this. So I can take the gamma square root. So rho 0 over rho 1 is this one to the power 1 over gamma minus 1. Yeah? So nice relations. Question? One slide back. Sorry. So nice relations between total conditions, and don't forget this is total conditions on the top, the current condition on the bottom, and the Mach number at this specific location. And it's not more information, it's just in different form, and it's sometimes handier if you have computed the Mach number or if you have information on the temperature to directly find the other one. Yeah? Is it okay? So then we have these and these from the isentropic flow relations. I think I have a summary slide. Yes. It's the same. It's gray, so it means that you really have to remember. On the exam, we might ask you to derive these from the energy equation and the isentropic flow. The only a bit tedious step, it's actually quite straightforward, I think. The only tedious step is these specific constants reworking I did on the blackboard. But if you remember that you have to start from this energy H is E plus PV, and you have to work your way to find a relation from Cp as a function of R, I think you should be fine. Should be. If you practice lots. Okay. I hope we have time for one practice. No? Oh, sorry. Okay, now what am I going to do first? Now, so I told you, you had to believe me, that we can assume incompressible flow for low speeds. You believe me? Good. I've been convincing. You can check now, right? So here you have a relation of how much the density changes with respect to total conditions as a function of the Mach number. And it goes squared. So you can imagine squared. So that is a parabola, right? So close to 0, it will not change that much. I will have the plot on the next slide. Close to 0, it will not change much. But further away from it, for higher Mach numbers, not close to 0, you have a stronger density change, right? So from this equation, I can directly show you what this density change actually is. Here I have the density ratio, so now I have to put it the other way around, rho over rho 0. So it is going down, so when the density becomes smaller than my total conditions, and here I have Mach number. So at 0 Mach number, my density is my total density. Up to Mach number of 0.3, the density, of course this incompressible flow assumption was an assumption and an approximation. In reality the density changes, but it doesn't change more than 5%. Up to Mach of 0.3. A Mach of 0.3, at standard sea level air conditions, the speed of sound is 340 meters per second. So a Mach of 0.3 is a third of that, so it's about 110 meters per second. But you see that if you are a bit faster, so you have Mach 0.32 or so 130 meters per second, it doesn't change as a drop discontinuously, but you see that the change increases, right? It becomes steeper. So up to around this, you can assume the density be constant. We neglect this couple of percent, but here you need to treat the flow as compressible. So around below Mach 0.3, so around below 100 meters per second. But if you apply it at 110 meters per second or 115, it will not harm you. If you apply it, if it's really your Mach number is 0.7, you have a problem. Because at 0.7 the density drop is 30%. And this of course is taken into account in the velocities and the pressures. Yeah? I will not make that. No. Okay, well I think I'll finish and then next time I'll start with 435. Any questions? Yeah. Okay.
Please visit our OpenCourseWare website for more information. See you at our next podcast.